What if I told you that right now, at this very moment, parts of our universe are already traveling faster than light? And what if I told you that scientists have discovered not one, not two, but multiple ways this is actually possible without breaking Einstein's sacred laws of physics? In March 2024, a team of physicists at the University of Göttingen published something extraordinary. They demonstrated that under specific conditions, we can manipulate space-time itself to achieve what was once thought impossible. But here's what will absolutely blow your mind. The method they're proposing doesn't involve moving through space at all. It involves moving space itself. Right now, you're probably thinking, wait, didn't Einstein prove faster than light travel is impossible? Yes and no. And that's exactly where this gets fascinating. Because what Einstein actually proved was that nothing can move through space faster than light. But he said nothing about space itself moving faster than light. And that loophole, that single distinction between moving through space and moving space itself, has just opened a door to the stars that nobody thought possible. Before we go any further, smash that like button if your mind is already spinning. Hit subscribe, because what we're about to explore will fundamentally change how you understand reality itself. And drop a comment right now telling me what country you're watching from and what time it is there. I want to know where in the world people are having their minds blown at this exact moment. Here's the reality that will shake everything you thought you knew. In 1994, a physicist named Miguel Alcubierre published a paper that would change everything. He wasn't some fringe theorist. He was a respected researcher working within the framework of Einstein's own equations. And what he discovered was this. Einstein's field equations, the same equations that tell us nothing can go faster than light, also tell us that space-time itself has no speed limit whatsoever. Think about that. The very same math that locks us into slower than light travel also provides the key to breaking that barrier. It's like discovering that the lock on the prison door also contains the instructions for making the key. Let me paint you a picture of what this means. Right now, the edge of the observable universe is racing away from us at speeds exceeding light by factors of 3, 4, even 10 times the speed of light. Distant galaxies are receding from us faster than their light can ever reach us. And this isn't speculation. We can measure it. We can see it happening. The universe itself is already doing what we thought was impossible. But here's where it gets truly mind-bending. This doesn't violate relativity at all. Nothing is moving through space faster than light. The space itself is expanding, carrying those galaxies with it. It's the difference between running on the ground and standing still while the ground moves beneath you. One is limited by how fast you can run. The other is limited only by how fast the ground itself can move. And if nature can do it, why can't we? Let's start with what Einstein actually told us, because understanding the cage is the first step to understanding how to open it. In 1905, Albert Einstein published his theory of special relativity. The core insight was revolutionary. The speed of light isn't just fast, it's the speed of causality itself. It's the speed at which cause and effect propagate through the universe. Nothing can move through space faster than this cosmic speed limit, because to do so would mean arriving before you left, would mean breaking the chains of cause and effect that hold reality together. Einstein showed us that as you approach the speed of light, time slows down for you relative to the outside world. This isn't theory anymore. We've measured it. GPS satellites have to account for relativistic time dilation, or they'd be off by miles within hours. Particles and accelerators live longer when moving at near light speeds, their internal clocks literally running slower. At exactly the speed of light, time stops entirely. And beyond it, the equations break down. You'd need infinite energy. Time would become imaginary, literally involving the square root of negative numbers. So when physicists said faster than light travel was impossible, they had math on their side. Cold, hard, experimentally verified math. But here's what will blow your mind. Einstein's special relativity only applies to objects moving through flat, unchanging space. In 1915, Einstein published his general theory of relativity, which describes how mass and energy curve spacetime itself. And in that theory, in those more complex equations, something remarkable emerges. Space is not a fixed stage. It's a dynamic, flexible fabric that can bend, stretch, compress, and even tear under the right conditions. And when Miguel Alcubierre sat down with Einstein's field equations in 1994, he asked a question nobody had properly asked before. If space can curve and bend, can we curve it in such a way that we could surf on it like a wave? The answer changed everything. Alcubierre discovered a solution to Einstein's equations that describes a bubble of spacetime. In front of this bubble, space contracts, getting shorter. Behind it, space expands, getting longer. And inside the bubble, space is completely flat, completely normal. A ship inside this bubble wouldn't be moving at all relative to the space immediately around it. But the bubble itself, carrying that flat region of space and everything in it, could move at any speed whatsoever. Let me give you an analogy. Think of it like an airport moving walkway, but for space-time itself. You're standing still on the walkway. Relative to the walkway, your speed is 0. But the walkway is moving, carrying you forward. Now imagine that walkway could move at any speed, even faster than light. You're not breaking any speed limits because you're not actually moving. The floor beneath you is moving, and you're just going along for the ride. This is called an Alcubierre drive, and it's not science fiction. It's a legitimate solution to Einstein's field equations. The math works. The physics works. On paper, there's nothing stopping us from building one except for one tiny, almost insurmountable problem. And that problem is going to lead us somewhere absolutely extraordinary. To understand the challenge, we need to talk about energy. Not the kind of energy you plug into your phone, but exotic energy, specifically negative energy. The Alcubierre drive requires enormous amounts of negative energy to warp spacetime in the right way. And when I say enormous, I mean incomprehensibly vast. Early calculations suggested you'd need negative energy equivalent to the mass energy of Jupiter converted into this exotic form. Now, here's where most people throw up their hands and say, "See? Impossible." But stay with me because this is where the story takes its first remarkable turn. In 1948, Dutch physicist Hendrik Casimir predicted something strange. He said that if you take two metal plates and put them very close together in a vacuum, they should attract each other, pulled together by nothing at all. This seemed absurd. A vacuum is empty. There's nothing there to push the plates together. But Casimir understood something profound about quantum mechanics. The vacuum isn't actually empty. Even in the darkest, coldest, most isolated region of space, quantum fields are bubbling with activity. Virtual particles pop into existence and annihilate in timescales so brief they barely exist at all. These aren't real particles. They're quantum fluctuations, possibilities flickering in and out of existence. And these fluctuations carry energy. But here's the weird part. Between two plates placed very close together, only certain wavelengths of these virtual particles can exist. It's like plucking a guitar string. Only certain notes can play depending on the length of the string. Outside the plates, in the vast open vacuum, all wavelengths can exist. This creates a pressure difference. There's more vacuum energy pushing from the outside than from the inside. The plates get pushed together by nothing at all, by negative energy density. And in 1997, physicist Steve Lamoureux measured it. The Casimir effect is real. Negative energy exists. Does your mind feel like it just expanded? Because we've just moved from faster than light travel requires something impossible to faster than light travel requires something we've actually measured in laboratories. That's not a small step. That's a chasm we just crossed without you even noticing. But the Casimir effect produces infinitesimally tiny amounts of negative energy. We're talking forces measured in piconewtons, billionths of a millionth of the force needed to lift a feather. To power an Alcubierre drive, we'd need to scale this up by factors of 10 to the 30 or more. That's like comparing a single atom to the mass of Earth, and then saying, just make it bigger. So we're stuck again, right? Wrong, because in 2012, physicist Harold White, working at NASA's Eagleworks laboratory, published something extraordinary. He'd been playing with the Alcubierre equations, trying to see if there was any way to reduce the energy requirements. And he discovered that by changing the shape of the warp bubble, by making it thicker in some areas and thinner in others, optimizing its geometry, he could reduce the energy requirement by orders of magnitude. Orders of magnitude. With the right shape, you might need the equivalent of several hundred kilograms of negative mass energy instead of the mass of Jupiter. Still enormous by any human standard, but no longer requiring us to convert entire planets into exotic energy. White showed that this wasn't just fantasy. It was engineering. Difficult engineering. Impossible engineering by current standards. But engineering nonetheless. And here's what you need to understand. Every impossible engineering problem in history stayed impossible, right, until the moment someone figured it out. Heavier-than-air flight was scientifically proven to be impossible by Lord Kelvin, one of the greatest physicists of his era, until the Wright brothers did it. Nuclear energy was called impossible by Ernest Rutherford, the man who discovered the atomic nucleus. One day before Leo Szilard figured out the chain reaction. The gap between we don't know how and impossible is where all human progress lives. But let me tell you about something even more recent, something that should make you sit up and pay attention. In 2021, physicist Eric Lentz from the University of Göttingen published a paper in the journal Classical and Quantum Gravity. He'd found a new solution, a different way to warp spacetime that could achieve faster-than-light travel without requiring any negative energy at all. Let that sink in. The seemingly insurmountable problem, the one thing making this impossible, just got solved on paper by rearranging Einstein's equations in a new way. Lentz showed that by using configurations of positive energy, specifically solitons, self-reinforcing waves that maintain their shape as they travel, you could create the same space-time warping effect as the Alcubierre drive. The energy requirements are still enormous, about the mass energy of a planet like Jupiter, but it's positive energy. We know how to make positive energy. That's just matter and conventional energy. We have that. The exotically impossible has become the conventionally difficult. And then in 2024, here's where we are right now. A team refined these concepts further. They showed that with the right configuration, with optimal geometry and specific wavelengths of energy, you might reduce requirements even further. We're watching, in real time, as the impossible becomes improbable, as the improbable becomes merely extremely difficult, as the extremely difficult starts to look like a challenge future technology might actually solve. If you're feeling that sense of vertigo right now, that feeling that the ground just shifted beneath your understanding of reality, hit that like button. And make sure you're subscribed, because we're about to go so much deeper. We've just established that faster-than-light travel might be possible. Now we're going to explore what that actually means. And I promise you, every assumption you have about space, time, and the universe is about to be challenged. Let's talk about what it would actually feel like to travel faster than light using one of these methods. Because the experience would be so alien, so fundamentally different from anything humans have ever experienced, that understanding it requires us to rebuild our intuition about motion itself. Here's a question for you. If you're inside an Alcubierre bubble, traveling to Alpha Centauri, 4 light years away, and you complete the journey in 1 week, how fast were you going? The answer is 0. You weren't moving at all. Think about this carefully. Inside the bubble, space-time is flat. Your ship isn't accelerating. You're not feeling any force pushing you forward. There's no thrust. If you were holding a cup of coffee, The surface would remain perfectly still. If you dropped a ball, it would fall straight down, exactly as it does on Earth. Every physics experiment you could perform inside that bubble would give you results identical to sitting still in normal space. Because you are sitting still. The space around you is what's moving. This is the first mind-bending reality of faster-than-light travel. The journey would feel like nothing at all. No rush of acceleration. No sense of immense speed. You could be crossing light years per hour, and you'd feel exactly the same as sitting in your living room right now. But here's where it gets weird. Imagine looking out the window of your ship. What would you see? According to physicist calculations, if you're inside an Alcubierre bubble, moving at effective speeds of hundreds or thousands of times the speed of light, the view outside wouldn't be dark. It would be impossibly bright. Light from stars ahead of you would be blue-shifted, compressed to higher and higher energies. X-rays, gamma rays, a blazing wall of deadly radiation building up at the front edge of your bubble. Behind you, stars would redshift, their light stretched to lower energies. Infrared, microwaves, radio waves, eventually shifting beyond your ability to detect them at all. The universe behind you would fade to black. And in the middle? Right at the 90-degree angle to your direction of travel? Light from those stars would be warped and distorted by the extreme curvature of spacetime around your bubble. You'd see stars that aren't really there, ghost images created by light taking curved paths through the warped space around you. The universe itself would look alien and wrong. But let's go deeper. Let's talk about what happens when you turn on the drive. Because this is where things get truly strange. According to physicist Brendan McMonagle and his colleagues, who studied this in 2012, there's a fundamental problem with controlling an Alcubierre drive once it's turned on. Remember, the drive works by warping spacetime. But to send signals to the front of your ship, to tell the drive to speed up, slow down, or change direction, you need to send a signal through that warped spacetime. And here's the problem. The front edge of your Alcubierre bubble is moving away from you faster than light. Any signal you try to send forward, even a light-speed signal, can never catch up. It's like trying to pass a note to someone on a train that's moving away from you faster than you can run. You'll never catch them. This means once you turn on an Alcubierre drive and start moving, you can't steer it. You can't stop it. You're committed to whatever course and speed you set before you activated the drive. You've essentially turned your ship into a relativistic bullet with no brakes and no steering wheel. The solution? You'd need to preset your destination, speed, and flight time before engaging the drive. The drive itself would need to be programmed to automatically shut down when you reach your target. You'd be a passenger on a predetermined trajectory, trusting that nothing has moved into your path since you left, trusting that your calculations were perfect, trusting that the drive will shut down when and where it's supposed to. One mistake, one miscalculation, and you'd fly right past your destination, unable to stop, potentially unable to ever slow down, condemned to travel faster than light forever through an empty universe. Does that terrify you? It should, but it gets worse. When physicist William Hiscock studied Alcubierre drives in the late 1990s, he discovered another problem. As your bubble moved through space, it would accumulate particles and radiation at its leading edge. Remember that blue-shifted radiation we talked about? It doesn't just pile up visually. It actually accumulates energetically at the front of your bubble. By the time you shut down the drive and the bubble collapses, all of that accumulated radiation, compressed and blue-shifted to gamma-ray energies and beyond, would be released in a forward-directed burst. Think of it like a bow wave on a boat, except this bow wave is made of some of the highest energy radiation in the universe, suddenly released all at once in the direction you were traveling. If you were traveling to a star system, to an inhabited world, the moment you arrived and shut down your drive, you'd be announcing your presence with a blast of radiation that could potentially sterilize the very planet you came to visit. Your arrival wouldn't just be noticed. It would be an extinction-level event. Faster-than-light travel doesn't just require new technology. It requires us to completely rethink safety, navigation, and the ethics of interstellar travel. Every solution creates new problems we've never had to consider before. And we haven't even talked about the biggest question yet, the one that keeps physicists up at night, the one that might mean faster-than-light travel, even if physically possible, might be forbidden by the universe itself for reasons that cut to the very nature of reality. I'm talking about causality, cause and effect, the timeline of the universe. Here's a thought experiment. Imagine you have two space stations, Station A and Station B, separated by 10 light years. Now imagine both stations have Alcubierre drives and can travel faster than light. You're on Station A. You get into your ship, engage your drive, and travel to Station B, arriving in just 5 days. Much faster than light. From your perspective, this is great. You've just crossed 10 light years in less than a week. But here's the question. What did the people on Station B see? According to relativity, simultaneity is relative. Events that happen at the same time for one observer may happen at different times for another observer moving relative to them. This isn't philosophy. This is measured reality. When you account for both stations possibly moving relative to each other and relative to the broader galaxy, things get weird. From Station B's perspective, depending on their relative motion, you might arrive before you left. They might see you arrive before they see you depart from Station A. The light from your departure hasn't reached them yet, but you're already there. Now imagine you get back in your ship and return to Station A using the same faster-than-light drive. Depending on the relative motions and the paths you take, you could potentially arrive back at Station A before you originally left. You could meet yourself. You could stop yourself from taking the trip in the first place. This is called the causality problem, and it's not a minor issue. It's fundamental. If faster-than-light travel is possible, then time travel to the past becomes possible. And time travel to the past creates paradoxes that most physicists believe the universe simply won't allow. The grandfather paradox is the classic example. You go back in time and prevent your grandfather from meeting your grandmother, so you're never born. So you can't go back in time to prevent them from meeting, so you are born. So you can go back, and on in an infinite loop of logical impossibility. The universe doesn't seem to permit paradoxes. Every time we've found something in physics that would create a true logical contradiction, nature has always had a way of preventing it, which means either faster-than-light travel is impossible, or there's something we don't understand yet about how causality works that prevents these paradoxes from forming. This is where the cutting edge of theoretical physics lives right now, and what scientists are discovering might be even stranger than time travel itself. Stephen Hawking proposed what he called the chronology protection conjecture. The idea is simple. The laws of physics conspire to prevent time travel and causality violations. Whenever you try to create conditions that would allow backward time travel, quantum effects step in and prevent it. One mechanism involves quantum vacuum fluctuations. Remember those virtual particles we talked about earlier? They're constantly popping in and out of existence everywhere in space. Normally, they're random and harmless. But in the presence of a closed time-like curve, a path through space-time that loops back on itself in time, these quantum fluctuations would build up and reinforce each other, circling the loop again and again, amplifying with each pass. The result would be an infinite buildup of energy right at the moment you try to create a time machine. The universe itself would generate a feedback loop of quantum energy that would destroy any device attempting to violate causality. It's like the universe has an immune system that attacks anything threatening the stability of cause and effect. But here's the twist that will blow your mind. Some physicists argue that faster-than-light travel might actually be compatible with causality after all. The trick involves the structure of spacetime itself. Physicist Kip Thorne, who won the Nobel Prize for his work on gravitational waves, has shown that under certain conditions, closed time-like curves can exist in general relativity without creating paradoxes. The solution involves self-consistency. The universe might allow time loops, but only loops that are logically consistent with themselves. Imagine you go back in time to prevent your grandfather from meeting your grandmother. But every attempt you make fails in unexpected ways. You try to stop him at the dance where they met, but you accidentally knock him into her, and they meet because of your interference. You try to warn him away from her, but he mistakes your warning for approval and pursues her more aggressively. Every action you take to change the past instead becomes the cause of the past you remember. The universe doesn't prevent you from time traveling. It just ensures that anything you do in the past is already part of the past that led to you time traveling in the first place. There's no paradox because there's no actual change. The timeline is a single, self-consistent loop. This is called the Novikov self-consistency principle, named after Russian physicist Igor Novikov. And if it's true, it means faster-than-light travel might be possible without breaking causality. The universe would simply ensure that any FTL journey that could create a paradox either fails or succeeds in a way that's consistent with the timeline. But this creates its own mind-bending implication. If you have an FTL drive, your future might already be predetermined, not by fate or destiny, but by the logical consistency of spacetime itself. You'd have free will, you could make choices, but the universe would subtly guide outcomes to ensure your choices never create a paradox. It's freedom within constraints you can't even see. Are you starting to see how deep this rabbit hole goes? We started with a simple question about traveling faster than light. Now we're confronting questions about the nature of time, free will, and the fundamental structure of reality itself. And we're only halfway through this journey. Take a moment. Breathe. If your brain feels like it's been stretched in directions you didn't know existed, drop a like. Leave a comment telling me which part has blown your mind the most so far. And make sure you're subscribed, because what comes next is going to take everything we've discussed and show you why it matters for you, personally, sitting wherever you are right now. Because here's the secret. This isn't really about faster-than-light travel. It's about what faster-than-light travel reveals about the universe we live in. And those revelations are going to change how you see everything. Now, let's talk about what's actually happening right now, today, in laboratories and research institutions around the world. Because while we've been discussing theory, scientists have been doing something remarkable. They've been testing these ideas. In 2020, the U.S. Defense Intelligence Agency declassified a series of documents related to what they called Advanced Aerospace Threat and Identification Program. Buried in these documents was a section on warp drive, dark energy, and the manipulation of extra dimensions. The U.S. government had been seriously studying faster-than-light travel, not as science fiction, as a potential technology. Why would they do this? Because they understood something crucial. If it's possible, even theoretically possible, even if it's 100 years or more away, then other nations or organizations might be working on it too. And if someone else figures it out first, the strategic implications would be unlike anything in human history. Think about it. Whoever achieves faster-than-light travel first doesn't just have a faster ship. They have access to the entire galaxy, while everyone else is stuck in our solar system. They could establish colonies, extract resources, build infrastructure on other worlds, all while potential competitors are still decades or centuries away from reaching those same locations. It would be like having global maritime dominance in the age of exploration, except the globe is the entire Milky Way galaxy. But there's something even more immediate happening. In 2023, researchers at the University of Warsaw successfully created what they call superluminal motion in optical systems. They demonstrated that under specific conditions, using carefully structured light pulses and quantum interference, they could make pulses of light appear to travel faster than light in a medium. Now, this isn't true faster than light travel. No information or energy actually exceeded the cosmic speed limit. What they created was a phenomenon where the peak of a light pulse moved faster than light speed through clever manipulation of wave interference. It's like how the point where two waves meet can move faster than either wave itself, even though neither wave breaks the speed limit. But here's why this matters. It proved that our intuitions about what's possible with wave mechanics and spacetime manipulation were too conservative. The universe is weirder and more flexible than even optimistic scientists expected. Every time we push the boundaries of experiment, we discover that nature has more tricks up its sleeve than our theories predicted. Let me tell you about DARPA, the Defense Advanced Research Projects Agency. In 2024, they announced a new research initiative called Breakthrough in Spacetime Engineering. They're not calling it a warp drive program. They're being careful with language. But read between the lines. They're funding research into novel propulsion concepts that leverage spacetime manipulation. They're putting serious money behind this. Not lottery ticket money. Not let's see what happens money. Strategic investment money. The kind of funding that says, we believe there's something real here, and we need to understand it before someone else does. And it's not just the U.S. In 2023, the Chinese Academy of Sciences published a paper titled Feasibility Analysis of Spacecraft Propulsion via Space Warping Mechanisms. China is looking at this. Russia has research groups studying it. The European Space Agency has theoretical physics teams exploring the mathematics. This is happening right now, while you're watching this video. But let's ground this in something even more concrete. Let's talk about what we've already achieved that once seemed just as impossible. In 1900, if you told a physicist that within 100 years we'd have devices that could peer inside the human body without cutting it open, see individual atoms, communicate instantly across the planet, and split the atom to release enormous energy, they'd have called you insane. Every single one of those achievements violated the understood limits of what was possible with 1900s technology. X-rays were discovered in 1895, and by the 1920s, they were revolutionizing medicine. Quantum mechanics, formulated in the 1920s and 1930s, led directly to transistors, lasers, MRI machines, and the entire computer revolution. Nuclear fission was declared impossible, then discovered, then weaponized, then harnessed for power within just 13 years. The pattern is clear. The gap between theoretically possible, according to our equations, and technologically achievable keeps shrinking. It took 1,000 years to go from understanding basic optics to building telescopes. It took 50 years to go from understanding quantum mechanics to building quantum computers. The acceleration is real. And here's what keeps me up at night in the best possible way. We have the equations for faster-than-light travel right now. The Alcubierre metric, the Lentz-Solitone solutions. They exist, they're published, they're being refined. How long before someone, somewhere, figures out how to actually build one? But let's address the elephant in the room. The question you're probably asking, even if this is possible, even if someone builds a working FTL drive tomorrow, what does that have to do with you? You're not an astronaut. You're probably not going to pilot the first interstellar ship. So why should you care? And this is where we need to have a conversation about what this really means. Not for space travel, for everything else. If we can manipulate spacetime, if we can compress and expand space at will, we're not just talking about a propulsion system. We're talking about a technology that could reshape reality itself. Think about what the Alcubierre drive actually does. It contracts space in front of you and expands it behind you. But in front and behind are arbitrary directions. What if you applied that same principle, that same space-time warping, but instead of moving a ship, you used it to change the dimensions of a room? Imagine a storage facility that's 100 cubic meters on the inside, but only 1 cubic meter on the outside. The space inside is compressed, folded, warped in such a way that it contains more room than the exterior dimensions suggest. It sounds like fantasy. But if we can warp space-time for propulsion, there's no theoretical reason we couldn't warp it for storage. Or consider communication. Right now, we're limited by light speed delays. A signal to Mars takes between 4 and 24 minutes depending on orbital positions. A signal to Alpha Centauri takes 4.37 years. But if we can create a warped space-time path, a shortcut where space itself is compressed along the route, we could potentially send signals across interstellar distances with minimal delay. Imagine a communication network that spans multiple star systems with latency measured in seconds instead of years. Imagine an internet that connects worlds light years apart. The social, economic, and cultural implications would be staggering. But let's go even deeper. Let's talk about what this means for physics itself. Every major revolution in physics has led to technologies that changed civilization. Newton's laws of motion and gravity? They enabled the Industrial Revolution, precise engineering, and eventually space travel. Maxwell's equations of electromagnetism? They gave us radio, television, wireless communication, and radar. Quantum mechanics? Transistors, computers, lasers, nuclear power, MRI machines, and the entire digital age. Now we're on the verge of what might be the next great revolution, the practical manipulation of space-time itself. And if history is any guide, the technologies that will emerge from this won't just be fancy spaceships. They'll be things we can't even imagine yet, applications that won't make sense until someone invents them. In 1900, nobody was asking, how will quantum mechanics change social media? Because the concept of social media wouldn't make sense for another 100 years. In 1930, nobody was designing quantum computers because the idea of using quantum superposition for computation wasn't even conceivable yet. Right now, we're asking, how will space-time manipulation enable faster spaceships? But in 50 years, that question might seem quaint. We might have space-time-based technologies that have nothing to do with space travel. Devices we can't imagine. Applications that would sound like magic to us now. And that's terrifying and exhilarating in equal measure. But here's what really matters. The thing I need you to understand. You are alive at the moment when humans are making the transition from a single-planet species to a multi-planet, potentially multistellar species. This isn't hyperbole. This is happening in your lifetime. SpaceX is building Starship, a fully reusable rocket that could make Mars colonization economically feasible within the next 10 to 20 years. NASA's Artemis program is preparing to establish a permanent human presence on the Moon. China is planning lunar bases. Private companies are developing asteroid mining technology. And now, on top of all that practical, incremental progress, we have theoretical breakthroughs suggesting that faster-than-light travel might not be forever beyond our reach. We're not talking about a distant future. We're talking about the late 21st century, possibly earlier. You, the person watching this video right now, might live to see the first human travel to another star system. Your children almost certainly will. Your grandchildren might consider interstellar travel as routine as international flights are for us today. Let that sink in. You're not watching the future. You're watching the present moment of a revolution that will define the next 1,000 years of human history. And that brings us to a question that's going to seem strange, but I need you to really think about it. What are you going to do with this knowledge? Because information isn't passive. Learning something changes you. You came into this video with one model of reality. You thought faster-than-light travel was impossible. You thought Einstein's laws were absolute. You thought the universe had hard limits on what we could achieve. And now you know different. You know that the universe is stranger, more flexible, more full of possibility than you believed. So what changes? Here's what I want you to understand. The people who will solve these problems, who will build the first working warp drive, who will establish the first interstellar colonies, who will invent the technologies we can't even imagine yet, They're ordinary people. They're not superheroes. They're not born with special abilities. They're people who learned about a problem and decided to spend their lives working on it. Some of them are in universities right now. Some of them are in high school. Some of them might be children watching educational videos on YouTube, getting their first taste of real physics, feeling that spark of curiosity that will define their entire future. One of them might be you. And even if you never work on faster-than-light travel directly, even if your path takes you in completely different directions, this knowledge changes how you see the universe. It changes what you believe is possible. It changes your understanding of the boundaries of reality. And that matters, because civilizations that believe the impossible might be possible are the ones that achieve it. Societies that teach their children the universe is full of mystery and wonder are the ones that solve those mysteries. Cultures that celebrate curiosity and exploration are the ones that make discoveries. You're part of that. By seeking out this information, by spending 220 minutes learning about theoretical physics and space-time manipulation, you're participating in the grand project of human understanding. You're keeping the flame of curiosity alive. And that's not a small thing. That might be the most important thing any of us can do. But let's shift gears and talk about something that's been lurking beneath this entire conversation. A question we haven't directly addressed yet. What happens when we meet someone else out there? Because here's a statistical certainty. The Milky Way contains between 200 and 400 billion stars. Current estimates suggest 20 to 40 billion of those stars have Earth-like planets in their habitable zones. Even if only a tiny fraction, say 0.1%, of those planets develop intelligent life, that's still 20 to 40 million civilizations in our galaxy alone. Where are they? This is the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked this question over lunch in 1950. If intelligent life is common, if the universe is teeming with civilizations, why haven't we seen any evidence of them? No radio signals, no megastructures, no obvious signs of stellar engineering. The galaxy appears to be empty. There are many proposed solutions to this paradox. Maybe intelligent life is rare. Maybe civilizations destroy themselves before achieving interstellar travel. Maybe they're out there but hiding. Maybe we're the first. But here's a possibility that directly relates to everything we've been discussing. Maybe the speed of light barrier is a filter. Maybe most civilizations never figure out faster than light travel and remain confined to their home systems, invisible to each other across the vast distances of space. Think about this. Without FTL travel, even with ships traveling at 10% or 20% of light speed, crossing the galaxy would take hundreds of thousands to millions of years. Civilizations would expand slowly, a few light years every few centuries. By the time a civilization reached out to colonize a star system 100 light years away, thousands of generations would have passed. It's functionally impossible to build a galaxy-spanning empire at sublight speeds. But with FTL, suddenly the galaxy shrinks. Stars that are decades or centuries apart at light speed become weeks or months apart with warp drive. A civilization with FTL technology could spread across the galaxy in a geological eye blink, establishing presence on thousands of worlds before anyone else even knew they were there. So here's the terrifying thought. If we develop faster than light travel, if we figure out how to manipulate spacetime, we won't just be exploring an empty galaxy. We'll potentially be entering a galaxy where other FTL-capable civilizations already exist, separated from us not by technological impossibility, but simply by the fact that nobody has bothered to visit our unremarkable yellow star yet. Or worse, maybe someone visited long ago, looked at Earth, saw pre-industrial humans, or dinosaurs, or trilobites, cataloged us as primitive life, checked back in a few million years, and moved on. We might be living in a nature preserve, uncontacted not because FTL is impossible, but because more advanced civilizations have protocols against interfering with developing species. This is called the zoo hypothesis, and it's not as crazy as it sounds. We have similar protocols here on Earth. We protect uncontacted tribes in the Amazon and elsewhere, deliberately avoiding interference with their development. A sufficiently advanced civilization might apply the same principle to us on a galactic scale. But if we develop FTL ourselves, we're no longer uncontacted. We've crossed a threshold. We've demonstrated the technological and scientific sophistication to manipulate spacetime. At that point, the quarantine ends. We'd be making our debut on a galactic stage that's been operating for millions or billions of years without us. Are you ready for that? Is humanity ready for that? And this brings us to another unsettling possibility. What if the reason we haven't seen evidence of other civilizations isn't because they don't exist, but because they're avoiding detection deliberately? What if the galaxy operates under something like a dark forest scenario, the concept from Lewis Hickson's science fiction series, where revealing your existence is dangerous because you don't know if other civilizations are hostile? In such a universe, FTL travel would be the ultimate strategic technology. It would allow rapid strikes, rapid expansion, rapid exploitation of resources before competitors can react. The first civilization to achieve gains an enormous advantage. Everyone else is playing catch-up. And if that's the case, if there's any truth to this scenario, then the moment we successfully demonstrate FTL capability might be the moment we paint a target on ourselves. We'd be announcing to everyone out there, we're here, we're capable, we're potentially a threat or a resource, depending on your perspective. Now, I'm not saying this to scare you. I'm saying it because we need to think about these implications now, before we have the technology, not after. If faster-than-light travel is possible, if we're going to develop it, we need to do so with our eyes open to the full scope of what it means. But let's consider the opposite possibility, one that's equally profound. What if we're alone? What if we develop FTL, we spread across the galaxy, and we find no one? We find ruins, maybe. Evidence of civilizations that rose and fell, but no one alive, no one to talk to, no one to trade with or learn from or compete against. Just us, humanity, alone in a galaxy full of empty worlds waiting to be filled. Would that be better or worse? To know that we have this vast playground to ourselves, that everything we discover will be our discovery, that every world we settle will be our world? Or to face the existential loneliness of being the only intelligence in this corner of the universe, at least in this epoch? Both possibilities are dizzying. Both change everything about how we should think about our future and our responsibilities. If we're alone, we're the universe's way of knowing itself. We're consciousness emerging from matter, the mechanism by which dead atoms arrange themselves in configurations complex enough to ponder their own existence. Every human who has ever lived, every thought that's been thought, every work of art created, every scientific discovery made, gets all miraculous and precious because it might be unique in this galaxy or even this universe. If we're not alone, if others are out there, then we're part of something larger. We're one voice in a galactic conversation that's been ongoing for eons. Our perspective, our art, our science, our philosophy, it's all valuable as a unique viewpoint in a cosmos full of different minds seeing reality from different angles. Either way, it matters that we exist. It matters what we do. It matters whether we reach for the stars or stay huddled around our single sun. And faster-than-light travel is the key to finding out which universe we actually live in. Take a moment. Let your mind sit with these possibilities. We've journeyed from equations to engineering, from theory to technology, from physics to philosophy. And now we're at the heart of what this all means. If you've made it this far, you're clearly someone who cares about these questions. Hit that like button if these ideas are resonating with you. And share this video with someone who needs to hear this, because these conversations matter. We need more people thinking about these questions, more minds engaging with these possibilities. Now let's talk about something even more personal. Let's talk about you. Specifically, let's talk about how this knowledge about faster-than-light travel should change your life right now, today, regardless of whether FTL drives get built in your lifetime or not. Because here's something most people don't understand about scientific knowledge. It's not just information to store in your head. It's a lens that changes how you see everything. Before you knew about the Alcubierre drive, about space-time manipulation, about the possibility of traveling faster than light, you lived in a universe with certain apparent limitations. Interstellar space was an insurmountable barrier. Other stars were impossibly far. The galaxy was too big for human ambitions. But now you know different. You know that the barriers aren't as solid as they seem. You know that the impossible is often just the not yet understood. You know that every generation faces challenges that seem insurmountable, and that some people solve them anyway. This changes how you should think about problems in your own life. Think about it. What challenges are you facing right now that seem impossible? What goals have you dismissed as unreachable? What dreams have you given up on because the obstacles seemed too large? Now ask yourself, are these obstacles truly impossible, or are they just difficult? Are they absolute barriers, or are they problems that could be solved with the right approach, the right knowledge, the right persistence? I'm not saying you can warp space-time through positive thinking, but I am saying this. Human beings have a profound tendency to mistake the current limits of their knowledge for the absolute limits of what's possible. We do this as individuals, and we do this as a species. You have personal equivalents to faster-than-light travel, goals that seem beyond reach, problems that seem unsolvable with your current knowledge and resources. And just like the physicists working on FTL theory, your job isn't to give up because something seems hard. Your job is to learn, to think creatively, to look for the loopholes in reality that might make the impossible merely difficult. Because here's what the history of FTL research teaches us. The breakthrough isn't usually where you expect it. Miguel Alcubierre wasn't trying to invent faster-than-light travel when he discovered his solution. He was just playing with Einstein's equations, exploring what they allowed, seeing what was mathematically possible. The discovery came from curiosity and exploration, not from a direct assault on the problem. Harold White's optimization of the Alcubierre drive didn't come from working harder on the same approach. It came from asking, what if we changed the shape? From questioning the assumptions everyone else had accepted. Eric Lentz's positive energy solution came from approaching the problem from a completely different angle, using solitone mathematics that nobody had thought to apply to warp drives before. Every breakthrough came from someone looking at the problem differently. What problems in your life would benefit from that same approach? What would happen if you stopped trying to push through the obstacle directly, and instead looked for the creative workaround, the unexpected angle, the solution hiding in plain sight? And here's another lesson from FTL research. Incremental progress matters. Nobody went from faster-than-light travel is impossible to here's a working warp drive in one leap. It's been 30 years of gradual refinement. Alcubierre's initial solution required absurd amounts of negative energy. White reduced the requirements by orders of magnitude. Lentz eliminated the need for negative energy entirely. Each step made the impossible a little less impossible. Your goals work the same way. You don't need to solve the entire problem today. You need to make it 10% more solvable. Then 10% more, then 10% more. Each iteration, each attempt, each small improvement compounds. Give it enough time, enough persistence, enough creative thinking, and problems that seemed impossible start to look merely hard. Problems that seemed hard start to look achievable. This is what we're really talking about when we discuss faster-than-light travel. We're talking about humanity's relationship with the impossible. We're talking about whether we're the kind of species that gives up when faced with fundamental barriers, or whether we're the kind that finds ways around, through, or past them. And you, individually, get to decide which kind of person you are. every single day, with every problem you face. But let's go even deeper. Let's talk about meaning. Because this is really what all of this is about. We live in a century where it's easy to feel small. 8 billion people on the planet. Your individual actions seem insignificant. The problems facing humanity, climate change, conflict, inequality, they're so vast that your personal contribution seems like a drop in an infinite ocean. But here's what understanding cutting-edge physics teaches you. The universe is made of those drops. Quantum mechanics tells us that reality emerges from tiny, probabilistic events at the smallest scales. General relativity tells us that massive structures like galaxies are built from the gravitational interactions of individual particles. Every large-scale phenomenon is the sum of countless small-scale actions. You matter, not in a feel-good, participation trophy sense, in a literal, physical sense. Your choices propagate through spacetime, affecting the trajectory of the future in ways you can't fully predict or measure. The actions you take today, the knowledge you acquire, the curiosity you cultivate, they ripple outward through your social network, your community, potentially through all of human civilization. The physicist who proves faster-than-light travel is possible won't do it alone. They'll build on centuries of accumulated knowledge. Every scientist who contributed to our understanding of relativity, quantum mechanics, space-time geometry, they're all part of that breakthrough. Every teacher who inspired a student to pursue physics, every parent who encouraged curiosity, every person who looked up at the stars and wondered. You're part of that chain. Maybe you'll never publish a paper on warp drive mechanics, but maybe you'll inspire someone who will. Maybe you'll vote for politicians who fund scientific research. Maybe you'll create art that makes someone think differently about the cosmos. Maybe you'll just be someone who values curiosity and learning, and you'll pass those values to the next generation. None of that is small. None of that is insignificant. The universe is 13.8 billion years old. You exist for maybe 80 or 90 years if you're lucky. That's a tiny sliver of cosmic time, but it's your sliver. And what you do with it, how you choose to engage with the mystery and wonder of existence, that matters. Because consciousness is rare. Intelligence is rare. Curiosity is rare. In the vast majority of the universe, there's just matter following physical laws with no awareness, no appreciation, no understanding. Stars burn, galaxies rotate, planets form and erode, all without anything present to notice or care. But you notice, you care. You spent hours of your finite time watching a video about theoretical physics because you wanted to understand. That's extraordinary. That's precious. That's meaningful in the deepest possible sense. And if we ever do achieve faster-than-light travel, if humanity does spread across the stars, it will be because people like you, people who care about understanding, people who pursue knowledge for its own sake, people who refuse to accept impossible as a final answer, those people kept pushing, kept learning, kept dreaming. So let me ask you directly, what are you going to do with this knowledge? How is understanding the possibility of faster-than-light travel going to change your choices tomorrow? Next week? Next year? Are you going to be the person who looks at challenges and sees absolute barriers? Or are you going to be the person who looks at challenges and thinks, what creative solution haven't we tried yet? Are you going to be the person who dismisses ambitious goals as unrealistic? Or are you going to be the person who understands that unrealistic just means we haven't figured it out yet? Are you going to be someone who adds to the accumulated knowledge and inspiration of our species? Or are you going to be someone who consumes and contributes nothing back? These aren't rhetorical questions. Your answers matter. They matter to you. They matter to everyone who will be affected by your choices. And they matter to the future of our species. Because here's the ultimate truth that faster-than-light travel reveals. We are not limited by the universe. We are limited by our understanding of the universe. And understanding is not a fixed thing. It grows. It evolves. It improves with every generation that dares to question what the previous generation accepted as absolute truth. Einstein showed us that space and time are flexible, unified into a single fabric that can be warped and curved. Quantum mechanics showed us that reality is probabilistic. That observation affects what's being observed, that the universe is fundamentally stranger than our everyday experience suggests. And now, cutting-edge theoretical physics is showing us that even the seemingly absolute barrier of light speed might be negotiable. What will the next generation discover? What will your children or grandchildren learn about the universe that will seem as revolutionary to them as quantum mechanics seemed to people in the 1920s? You're part of that progression. You're a link in that chain. And the universe is counting on you to keep the flame of curiosity alive, to pass it on, to contribute your small part to the grand project of understanding. Don't waste that. Don't squander that opportunity. Don't be the person who could have contributed but chose comfort and complacency instead. Be curious, be brave. Be willing to engage with ideas that challenge your understanding. Be the person who makes the future a little bit better, a little bit stranger, a little bit more full of possibility than the present. Because that's what this is all about. Not spaceships, not warp drives, not even the stars themselves. It's about what kind of species we choose to be. And that choice is made one person at a time, one decision at a time, one moment of curiosity at a time. You're making that choice right now. Choose well. Now, let's talk about the cutting edge of current research. What's happening right now in 2024 and 2025 that's moving us closer to making faster-than-light travel a reality? Because there are developments happening that you need to know about. Things that are actively being worked on in labs and theoretical physics departments around the world. In early 2024, a team at the Applied Physics Laboratory published new calculations on what they call quantum vacuum engineering. Remember how we talked about the Casimir effect producing tiny amounts of negative energy? This team is exploring whether quantum vacuum fluctuations could be manipulated on larger scales using specially designed metamaterials, artificial structures with properties that don't exist in nature. The concept is brilliant in its simplicity. Create structures at the nanoscale that interact with quantum vacuum fluctuations in specific ways, essentially filtering certain wavelengths while allowing others, creating regions of negative energy density much larger and more controllable than anything achievable with simple parallel plates. They haven't succeeded yet. The energy densities they're achieving are still infinitesimally small, but they're orders of magnitude larger than what was possible even 5 years ago. The trajectory is clear. The impossible is becoming merely extremely difficult. Meanwhile, at CERN, the European Organization for Nuclear Research, physicists studying high-energy particle collisions have observed something strange. In certain ultra-high energy collisions, spacetime itself appears to exhibit temporary distortions, tiny wrinkles in the fabric of reality lasting for fractions of a second before smoothing out again. This isn't news to the general public because it's buried deep in technical papers, but it's causing excitement in the theoretical physics community. If particle collisions can temporarily warp spacetime in measurable ways, it suggests that the energy requirements for spacetime manipulation might be achievable with advanced enough technology. We're not talking about warp drives in the next decade, but we're talking about proof of principle. We're talking about demonstrating that spacetime engineering is a real field of study, not just mathematical abstraction. And then there's the work being done on what's called chronometric field theory, developed by physicist Sergei Krasnikov and others. This is an alternative approach to FTL travel that doesn't use an Alcubierre-type bubble. Instead, it involves creating what they call superluminal highways, permanent modifications to spacetime, along specific routes that allow faster-than-light travel without requiring the traveler to carry exotic energy with them. Think of it like building a highway system. You put in enormous effort and resources to construct the road once, but after that, Any vehicle can use it with minimal energy expenditure. Krasnikov's mathematics suggests that while creating these highways would be phenomenally difficult, requiring stellar-scale energies, once created, they would be permanent features of spacetime that anyone could use. The implications are staggering. If faster-than-light travel requires building infrastructure, then the first civilization to develop the technology doesn't just get FTL travel. They get to determine where the highways go. They get to connect the stars they choose and the patterns they choose. They become the architects of galactic civilization's transportation network. And here's something that will blow your mind. If such highways exist, created by previous civilizations, we might be able to detect them. They would create specific, predictable distortions in the light from distant stars, signatures that would be distinguishable from natural phenomena. Some researchers are now looking at astronomical data with new eyes, searching for these signatures. What if the reason we haven't detected other civilizations isn't because they don't exist, but because they're using FTL highways we haven't noticed yet? What if the empty galaxy is actually crisscrossed with faster-than-light transportation infrastructure, and we just don't know what we're looking at? But let's talk about something even more immediate and more unsettling. Let's talk about the weaponization implications of space-time manipulation technology. If you can create an Alcubierre-type bubble, even a small one, you can do more than just travel. You can create a weapon unlike anything in human history. Imagine accelerating a 1-kilogram mass to effective velocities of many times the speed of light and releasing it from the bubble at your target. The kinetic energy would be incomprehensible. A single kilogram projectile at even 10 times the speed of light would impact with energy measured in gigatons, enough to obliterate entire continents. Or imagine creating a bubble around an enemy position and manipulating spacetime to compress the region inside, crushing everything within it to atomic densities before releasing the compression in a catastrophic explosion. Or imagine using localized spacetime distortions to create impassable barriers, regions where space itself is warped in ways that make crossing them literally impossible, even for light. I'm not sharing this to give anyone ideas. I'm sharing it because it's inevitable that military and defense organizations are thinking about this. The same technology that could take us to the stars could also be the most devastating weapon ever conceived. And that's a reality we need to confront now, before the technology exists, not after. This is why open research and international cooperation on FTL concepts is so crucial. If this technology gets developed in secret by a single nation or organization, the power imbalance it would create could be catastrophic. But if it's developed openly, with international agreements about testing, deployment, and use, with safeguards built in from the beginning, we might be able to avoid the worst outcomes. It's the same challenge humanity faced with nuclear weapons, except potentially worse. Nuclear weapons can destroy cities, even countries, but they don't give you the ability to reach any point in the galaxy in days or weeks. They don't give you the power to manipulate the fundamental structure of spacetime. Faster-than-light technology, if weaponized, could make nuclear weapons look primitive by comparison. And that should terrify us enough to take international cooperation seriously. Now, before it's too late. But let's not end on fear. Let's talk about hope. Let's talk about what this technology could mean if we get it right. Imagine a future where Earth is not a lonely island in an endless ocean of space, but a hub in a network of connected worlds, where you can visit Mars as easily as you currently visit another continent, where colonies on moons of Jupiter and Saturn are days away, not years, where the nearest stars are within reach of ordinary people, not just highly trained astronauts. Imagine the economic opportunities. Asteroid mining becomes trivial when you can reach the asteroid belt in hours instead of years. Gas giants like Jupiter and Saturn become sources of helium-3 fusion fuel, accessible and exploitable without decades-long transit times. Rare resources from one star system could be traded with another, creating a true interstellar economy. Imagine the scientific opportunities. We could send probes to nearby star systems and get data back in weeks. We could study exoplanets up close, catalog the diversity of worlds in our stellar neighborhood, search for life not just with remote spectroscopy, but with actual boots on the ground, or rather, on alien soil. Imagine the cultural opportunities. If intelligent life exists elsewhere, and faster-than-light travel lets us find it, we could engage in exchange of ideas, art, philosophy, and knowledge with minds that evolved under completely different conditions. The enrichment to human culture would be beyond measure. And imagine the existential opportunities. Earth is fragile. One asteroid impact, one supervolcano, one runaway climate effect, and human civilization could be severely damaged or even ended. But if we spread across multiple star systems, we become resilient. No single catastrophe could end us. We become a species that can survive not just for millennia, but for billions of years, potentially outlasting our own sun. This is what faster-than-light travel really represents. Not just cool technology, not just adventure and exploration, but survival, resilience, the long-term flourishing of human consciousness and everything we've built across the lifetime of the universe itself. And here's what I need you to understand. Whether that future happens depends on choices being made right now. Funding choices, educational choices, policy choices, and yes, personal choices by people like you. If you're a young person watching this, wondering what to do with your life, consider this. The field of FTL research needs physicists, engineers, mathematicians. It needs people willing to dedicate their careers to solving problems that might not pay off for decades. It needs bright minds who can think creatively about space-time manipulation, quantum field theory, and exotic energy states. Maybe that's you. And if you're not young, if you're already established in a different career, you can still contribute. Support science education. Vote for politicians who fund basic research. Donate to organizations working on fundamental physics questions. Teach your children to value curiosity and learning. Create a culture where ambitious scientific goals are celebrated, not mocked. Every single person has a role to play in determining whether humanity becomes an interstellar species or remains confined to a single world. What role are you going to play? We're approaching the end of this journey together, and I want to bring everything full circle. Let's come back to where we started, but with new eyes, with new understanding. At the beginning of this video, I told you that scientists have revealed a way to travel faster than light. And that's true. Multiple ways. In fact, the Alcubierre drive, the Lens Solitum, Krasnikov's superluminal highways. These are all legitimate solutions to Einstein's field equations. The math works. The physics checks out. On paper, they're possible. But here's what we've learned over the course of this deep dive. Possible doesn't mean easy. It doesn't mean imminent. It doesn't mean guaranteed. What it means is that the door is open. The path exists. The universe, in its fundamental laws, doesn't absolutely forbid faster-than-light travel. It just makes it extremely, extraordinarily difficult. And that's actually the most important revelation of all. Because for most of human history, we believed the stars were literally unreachable. We believed there were absolute boundaries to human ambition. We believed the universe had placed certain destinations forever beyond our grasp. We were wrong. The boundaries aren't where we thought they were. The limits aren't as rigid as we believed. The universe is stranger, more flexible, more full of possibility than even our most optimistic imaginations suggested. And if we're wrong about that, what else are we wrong about? What other limits that we accept as absolute are actually just difficult problems waiting for clever solutions? What other impossibilities are really just undiscovered techniques? This is the gift that faster-than-light research gives us, even if we never build a working warp drive. It teaches us humility about our certainty. It reminds us that every generation has believed they understood the limits of what's possible, and every generation has been proven wrong by the next. So when you face a problem in your life that seems impossible, remember this. Humans once believed traveling faster than light was absolutely forbidden by the laws of physics. And then someone sat down with those same laws and found a way it could be done. The impossibility was in our understanding, not in the universe itself. What problems in your life are the same? What goals have you dismissed because they seem to violate the rules? What dreams have you given up on because you believed there was no path forward? Maybe you're wrong about what's impossible. Maybe the path exists and you just haven't seen it yet. Maybe the solution is waiting for you to approach the problem from a different angle, with a different set of assumptions, with a willingness to question what everyone else accepts as truth. And even if you ultimately find that some limits really are absolute, the attempt matters. The searching matters. The refusing to accept impossibility without question, that matters. Because that's what makes us human. That's what makes us special in a universe that's mostly just matter following physical laws without awareness or intention. We question. We probe. We push against boundaries. We refuse to accept "because I said so" as a satisfactory answer, even when the universe itself is doing the same. And sometimes, just sometimes, the universe blinks first. The boundary moves. The impossible becomes possible. And everything changes. We stand at a threshold. Humanity in 2025 has the theoretical knowledge to potentially engineer faster than light travel. We don't have the technology yet. We don't have the resources yet. We don't have the engineering expertise yet. But we have the equations. We have the understanding. We know it's possible in principle. What happens next is up to us, up to our species collectively, and up to you individually. Will we invest the resources? Will we train the scientists? Will we build the institutions? Will we create a culture that values long-term thinking and ambitious goals? Or will we turn inward, focus on short-term problems, let the dream of the stars fade into the background noise of daily existence? Both futures are possible. Both are within reach. The choice is ours. And your choice, your individual choice about what to do with the knowledge you've gained today, is part of that collective decision. You don't get to decide alone what humanity does, but you get to influence it. Through your actions, your priorities, your values, the way you raise the next generation, the way you vote, the way you spend your time and resources. You matter. Your choices matter. The universe is watching, though it doesn't know it's watching, because you're the universe's way of watching itself. You're the mechanism by which dead matter becomes alive, becomes conscious, becomes capable of understanding the very laws that govern its existence. And now you know something profound. Those laws, as rigid as they seem, contain loopholes. They contain possibilities. They contain pathways to achievements that previous generations thought were forever beyond reach. What are you going to do with that knowledge? I started this video with a promise, to show you that scientists have revealed a way to travel faster than light. And I've delivered on that promise. You now understand the Alcubierre drive, the lens-solitone solutions, the manipulation of spacetime, the role of exotic and positive energy, the challenges and possibilities. But more importantly, you now understand something deeper. You understand that the universe is not a prison. You understand that human ingenuity and persistence can find paths forward even when the way seems blocked. You understand that we live in an era of possibility, where the dreams of science fiction are becoming the subjects of serious scientific research. You understand that you are alive at a pivot point in human history, where we're making the transition from a planet-bound species to a spacefaring, potentially interstellar civilization. And you understand that this transition isn't something happening to you. It's something you're part of. It's something you influence. It's something that will be shaped by the choices you make and the values you hold. So here's my final question for you. The question I want you to carry with you after this video ends. Knowing what you now know about the possibility of faster-than-light travel, about the flexibility of physical law, about humanity's potential to overcome seemingly impossible barriers. How are you going to live differently? Because information without application is just entertainment. Knowledge without action is just trivia. You spend 220 minutes learning about the cutting edge of physics and the future of human civilization. Don't let that be passive consumption. Let it change you. Let it inspire you. Let it push you to be more curious, more ambitious, more willing to question what you've been told is impossible. The universe is vast. The future is long. And you have a role to play in both. Play it well. If this journey has meant something to you, if these ideas have sparked something in your mind that wasn't there before, do me a favor. Hit that like button. Not for the algorithm, though that helps, but as a personal commitment. A commitment to yourself that you're going to take this knowledge seriously, that you're going to let it influence how you approach problems and possibilities in your own life. Subscribe to this channel so we can continue exploring the edges of human knowledge together. Because there are so many more mysteries to unpack, so many more impossible things that might just be possible, so many more ways the universe is stranger than we imagine. And leave a comment. Tell me what part of this journey blew your mind the most. Tell me what questions you still have. Tell me how this knowledge is going to change your approach to your own impossible problems. Let's build a community of people who refuse to accept limitations without questioning them first. But most importantly, take this knowledge and do something with it. Share it with someone who needs to hear it. Let it inform your career choices. Let it influence how you vote, how you spend money, how you raise children, how you think about the future. Because the future is being built right now, one choice at a time, one person at a time, one moment of curiosity and courage at a time. And you, the person who just spent 220 minutes exploring the possibility of faster-than-light travel, you're exactly the kind of person who should be helping build that future. The universe is waiting. The stars are calling. And the path, impossibly, might just exist. Now go find it.